let's try to solve another Leetcode problem. 2192. All ancestors of a node in a directed acyclic graph. So, a directed acyclic graph is called DAG. So this means it is directed, but there's no cycle inside this graph. If it is like that, so we're gonna say that it is a topological structure. Now let's try to understand it. So we have the nodes, it's going to be 0 to n-1, and it is a directed acyclic graph. And we are also giving a 2D integer array. As is I, it means from 2, so it means there's a direction from I to 2i in the graph. So we're going to return a list answer, where answer I is the list of ancestors of the ith node. So for example, let's just to check the 0th node, not 0. Yeah, because for node 0, there's no ancestors, so we're going to return an empty array. But for this node 3, it has ancestors of 0 and 1. So for node 3, it's going to have 0 and 1. Yeah. Maybe you think this is not ancestors, I need to reverse it. But this is according to the question. The structure is like that. So the direction is like that. But for this node 3, the ancestors is 0 and 1, because 0 connected to it and 1 connected to it. So we're going to understand it like this. Maybe it is just, it seems abnormal. Maybe it's going to reverse, but we don't need to reverse the graph. We just need to understand. So for the ancestors of 3, it is 0, 1. For ancestors of 6, it's going to be like 0, 1, 3, and 4, and 4. So let's just check ancestors of 6. So it's going to be 0, 1, 2, 3, and 4. Yeah, so that's going to be the ancestors. It seems it is a topological structure. Definitely we can use the topological sort to solve the problem. But we need to know about the relationship of each other. Maybe for the node 3, you can, let me use another color. So for this node 3, you can put a node 0 and 1 inside. But what about node 6? Can you put 0 and 1 inside? Maybe you can put 3 and 4 inside. So what about 0, 1, and 2? So this is the problem we have to solve. So how can we solve that? Maybe you're gonna try to think about it, use an array, and then remove the duplicate. But why not we just use a set? I mean, from here at this node 3, so we're gonna store the value as a set. So for this k is 3 inside a hash table, and now inside we're gonna prepare a set. So inside the set it's gonna be 0 and 1. So while we are checking this 6, and we got this 3, and we're gonna put 0, 1, 3 inside. So it's gonna be 3, 0, 1, and then we're gonna put 2 and 4 inside as well, 2 and 4. After that, we're gonna sort it because we need to return a sorted array for the result. Yeah. So if we know how to store the value by using a set, basically we can try to solve the problem. Yeah. We're going to prepare a graph and integrate. So the graph going to be a default dict, inside going to be list, and the integrate going to be 0 times n. Now I'm going to check all the edges. Yeah, so it's going to be G A should append B, and the integrate with B should plus equal to 1. Now I'm going to check the graph. So for the Q, it's going to be the Q I for I we in enumerate the integrate. So if this v equal to 0. Yeah. But how can we prepare the final result? We can prepare default dict. Yeah. Let me think about it. So we can prepare a set. Definitely we can prepare a set. So let's just prepare it like this maybe. So this is a hash table, and inside it's going to be I with a set. Yeah. So I'm not sure if you write it like this or you have the better way to write it. But for me, I would to prepare all the nodes. It is I, and its neighbors, its connections, I'm gonna put it inside a set. So So for example, for this node 3, I'm gonna put 0 and 1 inside. Yeah, so yeah, because I need to check the duplicate. If there's a duplicate, I need to avoid that. So this is why I would to use a set. So for I set, for I in range n, so this is a dictionary. So yeah, I prepare a Q and a dictionary. Now I want to check the Q. So while Q not fully equal to Q dot pop left. Yeah, let me just finish the basic structure. So for neighbor in G with this node, I'm gonna check the in degree first. Yeah, so for the in degree with this neighbor, if it is equal to it should be minus equal to 1. If this in degree with this neighbor equal to 0, yeah. So if it is equal to 0, I'm gonna put it the neighbor. I'm gonna put the neighbor inside of the queue. So this is the basic structure, but we didn't do anything about the final dictionary. Yeah, but finally we need to return the dictionary, but it's gonna be an array. So we're gonna use sorted with the list. Let me use maybe I'm gonna use maybe array, sorted list array. So for this array inside d dot values. Yeah. So d dot values is just a set, and we need to turn this set into a list, and then we're gonna sort it. Yeah, because we cannot sort the set directly, we have to turn it into a list. Currently it is okay for our result, but we didn't do anything about the dictionary yet, so this is going to be the difficult part. So currently we have this node. So for example, this is node 0 and its neighbor is 3, right? So its neighbor is 3. Definitely we're gonna put the neighbor. Yeah, so for this neighbor, we're gonna prepare an ancestor, so it's gonna be add to this node. Yeah, this is okay, but this is not finished, because we only put, for example, for this 3, we put a 0 and 1 inside, but what about 4? But what about 6? We only put 3 and 4 inside, we didn't put 0, 1, 2. Yeah, why not? Let's just check the result. Definitely it's gonna be wrong. As you can see, from the beginning it is okay for 0, 1, 2, there's nothing, it is okay, 0, 1, 2, but for 3 it is 0 and 1, it is okay, but for 4 it is 0 and 2, it is also okay. But what about this one? What about 5? For 5 we should have 0, 1, 3, but we only have 3, as you can see it. Yeah, and also for 6 we only have 3 and 4. And also for this 7, we only have 2 and 3, but we need to have 0 to 3, 0, 1, 2, 3. This means we didn't put other relationships inside. This is not enough. Yeah, this is why we're gonna use a set. As you can see here, for neighbors we're gonna add this node, but for this neighbor, yeah, for this neighbor we're gonna use the set or. I'm not the set union. So this is called the currently here. Yeah. So this kind of operation is called the set union. I'm not sure. There are two ways in Python to write it like that. One is the bitwise OR, another is the set union. If you use it like a set, because bitwise OR and set they are similar, so that is why they use the same sign. So currently I'm gonna use this sign as the set union. I'm gonna union them together. So d neighbor with this d node. So basically, so for example, let me just try to explain it. So for example, for d neighbor 6, right? Yeah, because 6 is a neighbor of 3, right? So for d neighbor 6, I put definitely I put 3 and 4 inside currently. Now I also want to put the d node inside. My d node is d3. d3 is 0, 1, so I put 0, 1 inside the set. I put 2 and 4 inside the set, but I will produce duplicate, because while I put 2 4 inside, 4 is connected with 0, I put another 0 inside. So this is why I need to use a set. I need to remove the duplicate, and by using a set, it's gonna be really fast. Even I used another on time, but it's gonna be really fast because we used the set. Yeah. If everything's okay, I think I can run it to Tag. As you can see, it works. Now let me submit it to Tag if it can pass. Yeah, as you can see, it passed and it's pretty fast. Let's analyze the time complexity. Normally for the normal topological sort, it is E plus V. So the number of edges plus the number of vertices, as the number of edges is 2000, so the number of vertices is 1000. So 1000 plus 2000, so we're gonna say it's just on time. But here is a set operation. So this kind of a set operation is gonna take on time. So this is why the time complexity is gonna be n squared. But while we are using the set, actually, this is gonna be really fast. I don't know why, but definitely it's gonna be really fast because this is the set union. Maybe for the set union, for average, we don't need to take another on time. So for average, maybe maybe while we are checking the neighbors, so for each of the neighbor, but the set operation is really fast. But the time complexity, I'm gonna say it as on squared, and basically this is another on time. It is a set operation. Yeah. So I will not explain too much about it because I don't know about why the set operation is so fast. Yeah. And thank you for watching. I think this is for today's problem. See you next time.